So we're going to solve a little problem now of a hand dryer used in public toilets. And what we're asked to find is the energy used by the dryer to dry our hands. And the manufacturers claim it'll dry your hands in 12 seconds. So let's draw a little picture of the arrangement. The schematic diagram doesn't need to be very precise. So it's got two air streams that come out which are fed from a single inlet. So these are my two air streams out, and the flow comes out here at a velocity of 200 meters per second, and the inlet here has a volume flow rate, so use capital V for that, of 32 liters per second. Okay? And we're told that the air around it is at room temperature, and that the difference in height between the intake here and the outlet is 30 centimeters. So we're going to solve this using the steady flow energy equation. So let's start out by saying we're going to apply the steady flow energy equation. And I'm going to make an assumption first of all. I'm going to assume air is an ideal gas. And so we can write down that m dot for the mass flow rate times the change in enthalpy between outlet and inlet plus the change in kinetic energy between the outlet and the inlet plus the change in potential energy between the outlet and the inlet will be equal to Q dot, the heat transfer rate, minus W dot, the work rate. Okay, so that's a standard result for steady flow energy equation. And we can say that this is adiabatic, there's no heat transfer going on, so no heat transfer, brackets adiabatic, therefore Q dot equals 0. So that removes that term. And if we look at these terms here, then the air is coming in at room temperature and it's going out at room temperature. There's no heating inside our air dryer, and so we can say that the process is isothermal. And hence there's no change in the enthalpy, so H2 equals H1, and so we can say that delta H equals 0. So this term will disappear as well. And then if we have a very large inlet here, we can assume that the velocity of the inlet is 0, so we can assume large inlet, therefore V1 is approximately equal to 0. And so we lose part of this term here. And so the remaining thing we need to look at is m dot here, and we can find m dot. So we can say now m dot will be equal to the density times the volume flow rate, and we're told what that is. So we can calculate this as 1.2 for the density of air times the flow rate over here, which is 32, and we'd like that in terms of cubic meters, so divide by 1,000, and that will come out as 0.0384 meters cubed per second. I'm sorry, that should be kilograms per second. Okay, so we can now substitute all these values into this expression up here. So let's call that equation 1. So substituting in equation 1, we're going to have W dot is equal to what's left over on this side here. So let's write it out in symbols first of all. M dot we still have, and this term here has disappeared. We're just left with one term here, so it's V2 squared over 2, and we're left with this term as well, plus G Z2 minus Z1, close brackets. And so we can put some values in here now, and we can say that m dot we've just found is 0.0384 times the velocity here, that's this value at the top, so that's 200 squared over 2, plus g, which is 9.81, times the height difference here, which is 0.3 of a meter. And if you get your calculator out and you work that out, you'll find that W dot equals 768.1 watts. So that's the rate of doing work, and so over a 12-second period, the energy used equals W dot times time, and so that's 768.1 times 12, and that's 9217 joules, and that's our final answer.